Thank you, Cindy. Welcome, everyone. I just want to preface this webinar with I got a new computer this morning. My computer crashed and some of the controls are a little different. So if this gets a little glitchy today, I apologize, and it's 100% my fault. But again, this seminar is going to be on automated mold production for composites using advanced additive manufacturing. And as Cindy said, I'm the composite specialist for North America. I have about 20 years experience in composites. So with that, we'll get going. So the title of the presentation today is going to be Transforming Manufacturing of Large Composite Parts, How They're Made. Give you a little background on Massivit. They were founded in 2013. They came out of Stealth in 2015. Our initial technology is called gel dispense technology. It's big and fast, and we have about 200 of those machines worldwide now in over 40 countries. We have more than 50 patents. The process is very fast for large parts. So, and it's very disruptive in different industries. So with that, we'll move along a little bit, and I'll explain more about the gel dispensing technology in a minute. But this, because we're a publicly traded company, I need to show you this safe harbor statement, which is basically saying we're not predicting the future. If you need to see this, we have a copy of it online. So here are some of the markets that Massivit is in. We're in automotive, marine, rail, aerospace, architecture, energy, signage, and that's just some of them that we're in with our initial technology, which is making large parts, large prototype type parts. And there's sub industries in there also, like in aerospace, it's commercial and government, and marine, it's commercial or recreational, but there's a lot of different things we're into. Excuse me, so we're going to do a poll question just so we understand the audience a little bit. Cindy, can you hear me?
I can hear you.
All right.
Our first poll question is, how do you currently make molds? The options are hand layup laminated fiberglass, CNC machining, additive manufacturing systems, or I do not manufacture molds. Please take a moment and answer right on the screen and let us know how you currently make molds.
So this is going to
looks like 44% of our responders do not manufacture molds.
Wow. So they may buy them from the outside, or they may just be curious of the technology. But this is going to help me shape my presentation a little bit. It's going to be broad in general for the entire audience, but it's nice to know what exactly is going on.
However, 27% use hand layup and laminated fiberglass.
Okay. So our research has showed that the hand laminated molds are the most popular, cost-effective way, but it's still very labor-intensive and takes a long time. So we can review this again towards the end if we need to, but let's move on.
Okay.
So whether you're machining a mold out of aluminum or tooling block, or using that tooling foam to make a master plug that you then make the laminated mold from, it's very labor intensive and takes a long time. So what we're hoping to do is take what you see on the screen here, which is some traditional manufacturing methods, and tighten it up. And what I mean by that is, right now, you go from CAD design, mold production to end part, and in a good year, it takes 5 weeks to make a mold. Sometimes it takes 8, 10, 12, 16 weeks. If you are purchasing the mold from a vendor that just makes molds, what I've heard is the wait time is up to 30 weeks. Some of these vendors that are making molds for other people won't take new customers. They're so busy. So that's infinite. So with that being said, if we break it down a little bit more, what we see, the mold building process of laminating a mold, excuse me, is from CAD design to having the mold ready to make a part is a minimum of 19 steps. And I would argue that it could be closer to 35 or 40 steps. It depends on how you define a step. What I mean by that is in the last step, number 19, prepare the mold surface. When you pull the mold off of the master plug, it still has to be buffed and polished, and then it needs to be sealed. So it needs to be cleaned up, and then it needs to be sealed. And then there's 5 or 6 steps of mold release on that before it's ready to make a part. So step 19 could be 5 or 6 steps. So what we're trying to do is we're trying to condense all these steps and remove as much labor as possible. So we're going to do that by automating the mold production. So CAD, 3D print, then you have your end part, which is not the part that's made from the mold, but the mold itself. So here we have, so we couldn't eliminate every single step. So what we have is we print it. And what we're using is a 2-part epoxy to make the mold. And I'll explain that a little bit more in detail. But you want to post-cure that epoxy so you have better mechanical properties. And then we need to somehow remove the outer material, what I call the shell, that formed the mold. And we have a special chemistry in the material that do that. It's a water breakable material. And then when you're done, you have a mold, but like any 3D printed part, it's not a high gloss finish. So the last step is to finish the mold, sand, buff, and polish. In some aerospace applications, our customers are machining the mold after it's 3D printed, and they're still saving a tremendous amount of time. So how does it work? This is where we're going to get into the nuts and bolts. The original technology we had was called GDP. I should say, gel dispensing technology. And what that does is it dispenses a very thick material, almost looks like toothpaste, and it's UV cured instantly. That's what you're seeing in the photo on the left. The material being dispensed, and there's a bank of UV lights that are curing it immediately. That's what makes it so fast. And you don't need any supports because it's hard instantly. It doesn't sag. So you could literally print a horizontal surface without supports with this technology. So great technology, big hollow parts, and that's where the light bulb went on with our founders and said, why don't we use that to cast a strong material, a 2-part epoxy? And that's what you're seeing happening on the right. So what we're doing is we're printing about 8 to 10, 12 layers, depending on the size of the part, of the shell material, the UV cured material. And then it stops, that head moves out of the way, and we fill that gap, that shell, with a 2-part epoxy. It has great mechanical properties, but one of the key elements or problems in 3D printing is the layers that you create in 3D printing makes for a weak part in the Z direction. By pouring a 2-part epoxy that has an open time of about 20 to 30 minutes, all those pour intervals blend together and we create an isotropic mold, which you can't do in 3D printing any other way. So we print a shell and then we cast some material in it. We do that time and time again until you build up the part. And when the other reason for doing it in intervals is because we're controlling the exotherm of the epoxy as it's curing. If we poured it all at once, it would exotherm all at the same time and you'd get cracks and warpage. So you see it here again, they flipped it over. So on the right, you see the UV cured gel. It's called Dim Gel 50 WB, water breakable. So the original material for the GDP or the gel dispensing printing is not water breakable. It's hard. It's like an acrylic. But we needed a way to easily get the mold out of the shell. So they changed the chemistry to make it water breakable. Now they don't say water soluble because it doesn't break down into the water. The water literally makes it swell up and fall off. And we'll show you some videos of this in a minute. So that's the dim gel 50 water breakable. On the other side is the cast in motion 155, or now we call it the CIM 500. It has a heat deflection temperature of 145 degrees C, just under 300, and it has a fairly low coefficient of thermal expansion. I know that's kind of ambiguous, but it's close to aluminum. It's around 25 parts per million for the CTE, and it's truly isotropic. We've had it tested by a third-party organization, and it's an isotropic mold. So the thermal expansion in the X, Y, and Z are exactly the same. The tensile strength under compression is the same in X, Y, and Z. And it's something that hasn't been done in 3D printing. Here's kind of a graphic to kind of explain why it becomes isotropic. In the left, what you see is if you're extruding a thermoplastic, you have this, I call it a barrier or a weak spot, which is between the extruding layers. That's always going to be a weak spot. Even in some of the industrial 3D printers that can extrude thermoplastic and they have a heated build chamber, the Z direction is much weaker. And if they're putting in strengthening agents like glass fiber or carbon fiber, it's only in the XY. As you're extruding it, the fibers line up, nothing happens in the Z direction. Where with our material, it all blends together. So you're seeing it cross-linking through the different pores, like cast 1, cast 2, cast 3, the different pore layers, and they're all blending together. So now I'm going to run a video, and bear with me with the technicals, but I'm going to run a video of what the system can do, the actual 3D printer. So let me see here.
Based on an initial CAD design, the first head 3D prints an outer sacrificial shell at high speed. The second head intermittently casts a thermoset material into that shell as it builds. The shell is comprised of two thin walls made of water-breakable photopolymer material that polymerizes instantly under ultraviolet light. The thermoset material forms a solid, isotropic mold. The mold can then be post-cured in an oven to improve its mechanical properties at elevated temperatures. It is then simply immersed in a bath of plain water, causing the shell to crumble away. The Massivit 10,000 offers near-net shape casting. Your high-temp, high-performance isotropic mold is now ready for use.
Okay, did that work? I mean, I saw it. Did everybody else see it? I sure hope so.
Yeah, look great, Mike.
Awesome, awesome. There is hope. Okay, so what that showed was the shell being printed and then the pouring. The shell being printed and then the pouring. So we're controlling the exotherm, what helps us be more accurate also. One of the typical questions I get from a prospective customer is, how accurate are your molds? And usually coming from the aerospace world, but we're about 1 millimeter per meter. And our system is rough standard dimensions. It's 5 feet in the X, 4 feet in the Y, and a little more than 5 feet in the Z. Our main product, the GDP printers, are 6 foot in the Z because we don't need as much height. We lose some height with the Massivit cast in motion machine because of the static mixer for the epoxy. So that being said, let's move it along. So the key benefits in our system is we reduce the time by 80%, labor cost by, well, if you're hand laying up a mold, and even if it's not a large mold, that's very, very labor intensive, from making the plug to gel coating it, to laminating the mold, to pulling it off and prepping it up. We reduce the labor tremendously, and we're reducing the cost also.
And Mike,
Now,
this might be a good time to launch our second poll about time.
Absolutely. So go ahead, read the second poll.
Second question is, how long does it currently take you to make mold? Is it less than 2 weeks, 2 to 4 weeks, 5 to 8 weeks, or more than 8 weeks? We'll just take a moment here.
Excellent question, and I apologize. I think this should have been a couple of slides earlier, but we're getting it in. This is great.
And 40% of our attendees are saying more than 8 weeks.
Not surprising. Again, it depends on the size of the mold, but it's not surprising. And like I said, if you go outside, some of the customers that are interested in this machine are the major composite tool builders in North America, and they're telling me that a standard mold is taking them 30 weeks to deliver. Not 30 weeks to make. You know, they can make their molds in 8 to 10 weeks, but they just got such a backlog that they can't get it to somebody in less than 30 weeks. So now I want to show you some samples of some of the molds that we've printed, and it's a good time to mention that this is a brand new technology. We have a beta customer in North America. We have a beta customer in Europe. We have a beta customer in Israel. It's been fully vetted. We have reservations in the tune of something like 25 reservations, and we're starting to ship machines. So it's a new technology, but it's real. It's fully baked in. We have some wrinkles that we're working out, but nothing that's slowing us down from shipping machines. So here is a mold for a race car seat. On the left, you see the as printed mold with the shell material on it. The center photo is showing you the mold with the shell removed, and then a part that's made from that mold. What I like to point out is the support structure that you can print into the part to save you even more time. A lot of times you'll get a mold and then it'll be backed up with square metal tubing, or 2x4s, or some other structure to make it a little more rigid and easier for the operator to make parts on. You can put those features into the mold with the printer, so when you remove the shell, you have those legs already on the part. Now, here's the dimensions of that mold, but more importantly, it took 42 hours to print. So typically, after the print, it's, regardless on the size of the part, it's going to take 10 hours to post-cure to get the mold material to ideal mechanical properties. And then it takes somewhere around 24 to 30 hours to remove the shell. You just put it in a tank of water. There's no chemistry, there's no caustic chemicals that are breaking down the shell material. It's just tap water. There's no heat, there's no agitation. You just let it soak. If you're in a hurry, after about 8 hours, you can start to pull the shell off. It's soft and gooey. But if you wait the full 24 to 30 hours, the shell material fell off the part. It's resting in the bottom of the tank. It can be strained out of the water, dried, and thrown away as a non-toxic, inert waste. So it's not something that you have to, it's biohazard at all. It's inert. You could use it as a filler, an asphalt if you wanted to, if you want to recycle it, but it's not toxic. That's the main point. Here's a print for a fairing on a motorcycle, and I think we're going to show you that one too. No. So here's an example of the, on the left, of the as printed part, and on the center what you're seeing is the part as it's breaking down in water. It's just slowly swelling up and falling off the part. And what you see on the right is the as printed mold. It had to be cleaned up to make it a true mold. What I mean by that is smoothed on the actual area that is the mold surface, not the backside or the flange, but the actual mold surface has to be sanded, buffed, and polished. And that's what you see there on the left. I'm sorry, on the right. So you also can combine certain features of the mold to have a tool in there. And what we mean by that is, here's a bicycle seat mold. And what we did is we mounted some inserts into the table, and then we printed around that. And what that enabled us to do is we now have a good datum in the mold for finishing machining the mold. We also added some clamping features on the mold so that when you're machining it, you have a place to grab. So there's a lot of flexibility in creating features on the mold to make manufacturing easier. And it all can be done in the printer. Here's another example. We have an aerospace customer that needed a washout mandrel. So the challenge here was, how do you get this core or this mold out of an odd-shaped part, a ductwork or something? So on the right, what you see is the 3D printed soluble material as printed, no epoxy, just the 3D printed material. And then they make the part on the mandrel, on the part that was printed. And when the part is fully cured, you can then soak it in the water and remove the mandrel from the part. Here's another graphical representation of a mandrel that you could not get out any other way but breaking it up or dissolving it in some way. Here is the mandrel. They did have to clean up the surface because it's as printed, and a 3D printed part has those layer lines, so they smoothed it. And here they're starting to lay up the part, and then they bag the part. And then they soak it in the water. So that's the breakdown, and what you have left is the part that you need. Now, I want to pivot just a little bit because our core technology of gel dispensing allows companies that don't even want to make a mold. They just want to make a part. So you can take, now it's a different machine. It's not the machine that makes the mold. The machine that makes the mold is called an M10000. It's a mold tool builder. That's what it's designed for. It only runs the water-soluble material, water-breakable material, sorry, and the epoxy. But our original technology of gel dispensing allows you to do things like make a console for a boat or a center console or a helm that maybe the customer is handicapped and he has certain ADA requirements, or maybe he just wants features in a certain way and you don't want to make a mold just for one customer. You can 3D print that part and then glass over it, gel coat over it, and you have that part there. I know there's other traditional ways of doing that. This is a lot faster. Some of the custom end-use parts that our customers are using. On the left, you see Velum Nautica. They wanted to extend the sidewall of the boat onto the swim platform to cut down on the amount of splashing that was going into the salon. They did that by 3D printing a part, bonding it to the boat, finishing it with gel coat. It's fully fiberglassed and looks like it was designed that way. We also have some legacy rail parts for Alstom that they don't have the molds anymore to make these parts. We 3D printed it. The 3D printed material is fire retardant. You glass over it with fire retardant resins and pretty it up, and now you have a part and you don't have to make a mold for that one part. Some more examples of what Velum Nautica is doing for marine, a special design part that they're going to bond onto a boat. And you also can see on the right here another part that Alstom was designing. Some other things that our customers are doing is special ground effects for automotive, special lighting or furniture. The concepts are endless. And on the full right there is a full-size car door for an automotive manufacturer who is prototyping different designs. So instead of making it out of clay or tooling board or 5 parts on a previously large 3D printer and then having to bond them all together, you can print it in 1 part on our machines. Here's some scenic fabricators that are doing some exotic stuff. Again, this is what our initial material. It's not why you joined the seminar, but I just thought it important to show you a little bit about what our technologies can do. And here's the industries we're in right now with the GDP and the cast in motion technology: aerospace, defense, infrastructure, marine, just about all of them. And there's a lot of subsets in there also. So with that, we want to show you a video of the machine in action today in Israel. It was going to be a live demo, but because of the time difference and some other technical issues, we had to make a recording instead. So I'm going to see if I can do it like I did the other one. So hang on with me here. Okay.
Hello everyone and welcome to Massivit headquarters in Israel. My name is Nir Dvir and I'm going to take you to a short tour understanding the Massivit 10,000 technology as well as some application that we can already show today. Our vision at Massivit 3D is to digitalize mold manufacturing for composite material using additive manufacturing. Additive manufacturing has a lot of benefits. We would like to add another important benefit to all the benefits. And here we talk about speed. The Massivit 10,000 is manufacturing molds within days instead of weeks. This is the Massivit 10,000. Let's dive into the technology. Allow me to show you step by step how the Massivit 10,000 is doing it. The Massivit 10,000 is using a dual head system. The first head is a dispenser. As you can see here, there is a big screw inside that is pushing material, the demon gel, through a tip which determines the resolution of the print. We are printing gel. The gel is sensitive for UV and will be cured by UV ring, as you can see here. Okay, I will try to focus it. Yeah, that's good. You can see 2 rings that will give you the optimal UV intensity for optimal drying. It does mean that if we cure with UV light, that we can print 1 layer on top of each other at the same way as we are printing 1 layer next to each other without using almost any support or infill to support the roof. It means a lot of material saving, a lot of time saving for the post-process. So this is one head. We talk about dual head technology. The second head we are talking about is a casting head. This is a mixer where part A and part B of the epoxy casting material will be poured in and cast into the gel dispensing printing material. How does it look? To give it more in picture, more explanation. As you can see here, with the first head, with the gel dispensing printing, I'm printing the shell, and at the second process, just immediately after that, we are getting the epoxy casting material cast into between those shells, actually creating a sandwich process. From the other side, we can take a look. how it looks. At the end of the process, we'll put it into an oven for a full curing and dip it in water. What is happening when we dip it in water? The shell will crumble off, and I will remain only with the epoxy casted material that was casted before. This is how it comes out of the Massivit 10,000, and this is how it comes after it is polished. And of course, you want to create composite material. So this is about the technology, and in order to do it, we talk about a print volume of 44-inch by 56-inch and approximately 59-inch height, or if we talk about centimeter, approximately 1 meter 10 by 1 meter 40, and the height of 1 meter 50. In order to operate the Massivit 10,000, you need, of course, the unit itself, as you can see it behind me, but also a casting unit that is standing by the Massivit 10,000, which we are going to see in a few minutes. We talk about mold manufacturing, and I want to show you a few samples done by the Massivit 10,000. Here we see a mold that was printed within hours. Okay, a mold that was printed within hours. You can see it, of course, after we remove the shell and polish it. The part that came out of this mold. But when we talk about Massivit 10,000 mold manufacturing system, you have also the capability, the ability to produce more than molds. You can also produce mandrels. I'll bring one sample with me. This is a mandrel, of course, a small one that was printed within minutes or a few hours, depends on the size, and it is built only out of the water breakable. No casting material, no epoxy casting material. Okay, so this is a mandrel, actually a mold that will be not dissolved but will crumble off with water. So you print it, hand lay up with your textile, dip it in water, and you will remain with your part within day. Imagine to produce a part out of composite material at the same day. Of course, the process include standard procedures, as you know, with the vacuum bag, and this is here, of course, only as an example. With the Massivit 10,000, we are talking about open molds, as you just saw before, but also closed mold for rim process. As you can see, sorry, I cannot pull the two of them together, but you can see one part of a compression mold that creating here actually this composite material part. Another application that is doable with the Massivit 10,000 are end parts. So if you need end parts, you can produce those end parts with the Massivit 10,000. Or if you want to create toolless, product, you can also hand lay up our GDP material and leave it within your product, and by that get the strength for your toolless product. What I suggest that we will try and focus and get to see both the both technologies, the dual head technology, and see the casting motion process that is happening within the machine. You can see the dispenser here. You can see the tip that is determined the resolution, and you can also see the UV ring with the two different rings in order to give the right intensity. You can see here just a mold that we are printing here. I'll come back to that. And we can see the mixer, actually the casting head, where part A and B are coming and just getting mixed at the right time when needed. Okay, if I will just put my camera on top here, you will be able to see it's very difficult for me to show, but I'll try. You will be able to see the shell and the casting area where we do the casting. This entire process called casting motion, because we cast as we go. Okay, again, the table, as you can see here, we can close and continue the printing later. Important to say about when we talk about casting material, we talk about high quality casting material. We want to have an isotropic mold, a mold that will expand evenly in all directions, X, Y, and Z. And the casting motion technology, the way we cast the material, enable us to create the isotropic behavior of the machine. We do want to see the printing process. What we can see here, we can see, if you can see the purple light, this is the UV ring that is curing the gel. You can see that the head is moving aside, and now the casting head is going into action. And casting material, part A and B of the epoxy, will be merged and mixed at the machine, at the printing head, and a lot of epoxy will be casted between the two walls that were just created by the first head. So a dual head technology, the first head is creating the shell, the space for the casting process, and then casting high performance material between those two walls. Once this process is ready, we will see the printing head going into an action again and printing the next layers again and again. We will now present also the mixing system, what we call CMS, where part A and part B are getting ready for the casting process during the printing. So next to the Massivit 10,000, you will always find another unit. This is our CMS system. At the CMS system, you will find mixer or preparation for part A and B of the epoxy casting material. Right temperature, right viscosity will make it ready to be sent to the Massivit 10,000 on time and mixed just when I need it. If we already talk about the material, we talk about high quality epoxy material, we talk about low CT, high HDT, creating at the end your isotropic mold for composite material. So that brings us to the end of our tour. I hope that you were able to understand the technology, to capture as much as we wanted to share. And of course, if you have more questions, we'll be very, very happy to support you with answers. Thank you again for your patience and for being with us.
Okay, sorry, I had myself muted there. So I thought that was great, a little long, but I thought it was important to see the parts and not just see it on a slide deck in a presentation. Nir does a very, very good job of showing all the different details, and I really appreciate his help. Okay, so we're almost towards the end here. Let's see what else we got going on here. Questions and answers. So at this point, Cindy is going to read out any questions that the audience has submitted, and I'll try to answer them. If not, I'll get your name and I'll get an answer for you and get back to you as soon as possible. Cindy?
We did have a few questions come through.
Okay.
At what temperature can the mold operate?
Up to 300 degrees F, or that HDT of 145C is what you can do. The glass transition temperature of the mold material is higher, but you don't want to get to that point where the glass transition of a material, it starts to get wonky, it starts to get gummy. So the answer is 145C, or just under 300F.
Okay. All right, another question here. Can you bond two 3D printed molds together?
Yes. So the short answer is yes. We have done that using our epoxy as the bonding agent, and it's worked just fine. Some of our other initial customers have shown interest in doing the same thing. They're identifying a couple methyl methacrylates that they want to use that are specifically adhesives. The challenge is just to make sure that the adhesive has very similar CTE to the mold material, so you don't want that CTE mismatch, and that's going to create a crack. So we've also identified some coatings to reduce the amount of time needed to finish the part to mold quality. We have a couple self-leveling materials from a third party that make the part look great with some hand sanding before, but not crazy, not 5-6 hours, not even an hour of sanding. Just a quick sand to break down the high parts, and then you spray coat it, sand the spray coating a couple times, put a clear coat, not a hard coat on top of that, and it looks like a gel coated mold. It looks really, really good. Now, if you had a CTE mismatch in a bonded part that you coated afterwards, it's going to crack right along that bond line. So that's the reason it's so critical to have an adhesive that has the same physical properties as the mold material. That was the longer answer.
How many parts can be manufactured with your 3D printed mold?
Okay, that's an unknown right now. It's a new technology. We've made, I would say, under 100 parts on a mold, probably closer to 50 of the bike seats and of the actual bike seats. But I've gotten input from some mold tool builders that are making laminated molds, and the sample molds that we show, the bike seat molds, are heavy. The specific gravity of the material is 1.8, so it's heavy, it's dense, and we're eliminating some of the problems that people have with laminated molds, which is air gaps and air pockets. The best mold makers in the world have to be really tedious to make sure there's no air bubbles or air pockets in the lamination or against the gel coat. That's gone with this process. So we're sure it's good for hundreds. We think it's going to be good for thousands of parts. We're not planning on doing accelerated life cycle testing on it, but we are getting a mold into a production facility in the next few weeks, and we'll report back. But it looks good.
Got a few more for you here. Could you elaborate on the labor and process of achieving smooth mold cavity surfaces?
Sure. So something like a bike seat mold, it would take you about half a day. You would sand it with 120 grit, and then you'd go to 220 500, and then you start wet sanding with 1,000 grit, maybe 800 grit to 1,000 grit until you get a nice smooth surface. You might want to get some buffing compound on there, depending on how visual the part needs to be. The better the mold, the better the part's going to come out. The machining time to machine that bike seat mold was a couple hours. From setup to finish was a couple hours. But where we've gotten some feedback from our initial customers that said if I have to machine the mold, it's not as compelling of a solution. So we've identified a couple customers, companies out there that make coatings specifically for 3D printed tools. And with a quick sand, on the bike seat mold, that would take 5 minutes of 120 grit just to knock down any high areas. You'd spray it a couple. You could do that with the spray coating and get it ready to be a mold in a couple hours maximum. And I'm exaggerating. You probably could do it in an hour. So depending on your tolerance accuracy you need on the part and the surface quality finish, really depends on how long it's going to take. We typically say about 1 or 2 days to print. If you're using the entire build envelope of our machine, it's about a day and a half to print, depending on the geometry. It's 8 to 10 hours to post-treat. So let's call it 2 days to print, 1 day to post-cure, 1 day to remove the shell. So right now we're at 4 days. And then give yourself 1 full day to finish the mold so that it has a mold quality to it. So in 5 days, you have a mold ready for production.
Next question. Your system is impressive. Thank you. Do you provide full material specification sheets so I can determine if the strength of your material will be applicable for my application? Is it possible to modify one of your base materials?
Okay, so the short answer to the tech data sheets are available for this material called SIM 500. And it's in constant development. And to put a finer point on that, I joined Massivit June 1 of 21, and they had a material called SIM 120. By September, they had SIM 140. By the fall, pretty close to December, they had SIM 155. Now they have SIM 500. So our goal is to have a material that can operate in an autoclave at 180 C and be stable like aluminum at that 25 parts per million CTE or less. That's our goal. So we're putting modifiers in there. We're doing things to get there. That's kind of a longer answer, but I can supply the tech data sheet, and where our goal is to become autoclavable.
And Mike will provide his contact information at the end if you want to reach out to him and get that information. Yeah. You mentioned fire resistance. What is the flame spread and smoke index per ASTM E84?
That's a big question. That flame reference was to our original technology called the GDP. I'm not a specialist there, but it does have a flame, smoke, and toxicity rating with UL. And I can get you that information for that particular material that is flame retardant. But the mold material hasn't been tested for that. That's important to mention.
And that question is asked by the same attendee. So you can reach out to him.
Okay.
Next question. What is the spray coating and what is the heat tolerances with that coating?
The heat tolerances match up to the tooling material, our epoxy. So it's rated at about 150 C. The materials is from a company called True Design. They've worked a lot with Oak Ridge National Lab in Knoxville, Tennessee, and True Design is also located in Knoxville, Tennessee. So their chemists have put this together. Initially, it was because Oak Ridge National Lab was 3D printing a automobile, and after 3D printing, to machine it, they were having tremendous problems. They were having a lot of breakage of the part because of the weak bonding in the Z direction. So it would start to break and chip out and delaminate. So they developed this coating to be able to spray coat the automobile and then machine it and then sand, buff, and polish. We don't need the first two, which was a heavy build material to fill in a lot of voids from other 3D printing processes. But so there's a TD sand, TD coat, and TD seal. The TD coat goes on a little heavier than paint. It's like gel coat, it's thick, and it's sandable. So it's almost like a Duratec primer. It's a sandable primer, and it can be buffed up. And then the clear coat on top of that is the hard coat that has been tested to be slightly harder than tooling gel coat. So tooling gel coat is on the Barcode Shore D scale of about 85, and this has been tested at about 92 Shore D. They do have some plasticizers in the coating that helps on that expansion. We don't need that because we're isotropic. They put that in there because the traditional method of 3D printing, the materials move very differently in the X and the Y than they do in the Z. So because they're so different, they needed to put some plasticizers in there to compensate for that uneven movement. And I can get you the tech data sheets and contact information for the coatings company too.
And that was the next question. Are you at liberty to provide the manufacturer or the product name of the spray coating?
Absolutely. We are not private labeling the finish coating.
Okay.
The tooling epoxy is our formula, our secret sauce, and we sell that direct. The coatings are going to be third party that we'll partner with, and we can even, when we do the benchmarking process, work with them to coat the sample so that you have a mold tool quality surface.
Have any of your early beta sites applied the molds to casting urethane?
So I want to say yes, but it was polyurethane foam, because I know there's another cast urethane that is strong and hard. So there's two different chemistries there. I think one's PU and one is PC, DC, or something like that. So the answer is yep, they've done it. As a matter of fact, the one that's doing the foam made a comment to us. It was just an offhand comment that when they evaluated our mold, the initial view, they said, this is the best 3D printed mold I've ever seen. Now, we did some coating on it, so it looked nice, and maybe whatever he saw before that from the competitors didn't have the coatings, but it was a great compliment.
It is a great compliment. And finally, will a video of this webinar be available for participants?
Yes, yes, it will. On that note, let's go to my information page. Oops, I just did it wrong, didn't I? So actually, I want to say, what are the next steps? If you're interested in our technology, we don't want to jump in head first. What we'd like, if you're interested, is to identify a CAD file of a mold or a part, and we'll do a time and material study. So our application engineering team will look at your part, they'll simulate it in our machine, and they'll put a report together that says your part took, well, first they'll show you some CAD renderings on how the part would be orientated in our printer, and then they'll tell you it took 17 hours, it used 15 kilograms of material, and what I'll add to that is the breakdown on what the shell material cost and what the epoxy material cost is, and you can make an evaluation that in 5 days and 25 or 15 kilos of material, I got a part, this is the system for me, or no, it just doesn't work for me, and we're fine. So after we review the time and material study, That's when we decide if we want to make an actual sample for you because you think you're interested in the machine or not. And we'll do that all the way up to the application review, free of charge, to make sure this is the right fit for the right customer. So here's my email address. Reach out to me anytime, and I can come in and do a presentation for a larger audience within a company, or we can just work virtually through the file transfers, and we'll do the time and material study. Any way you want to work, we'll do it. We really believe in this technology moving forward is revolutionizing the composites industry to get to market faster. In addition to reducing the cost of the mold and doing it quickly, if the mold price is less, you can do lower run parts, you can iterate faster, you can offer your customer more variations for less exorbitant pricing, if that's a word. So thank you very much. I think we almost went over time. If there's any other questions, please email me, and we will be sending out information to anybody who's interested, and I believe this presentation will be available for anybody who would like it. Thank you very much and have a great day.